Hey guys, so today welcome to 3.1 Energy Sources and Thermochemistry. So we're going to be talking a little bit about energy, the different types of energy available, and how basically energy is transformed when we have reactions. We're going to talk a little bit about reactions in general, what type of reactions release energy into the environment, so they release heat into the environment, what types of reactions absorb heat from the environment, and how we can classify that, how we can describe that, and how we can visualize that. Okay, so we can think of energy as the capacity to do work. And if this sounds a little vague, well, that's okay, because there's lots of different types of energy that we'll talk about, and we'll find that this definition is the one that really just holds true throughout all the different types of energy available. So when we talk about energy, when we talk about work, what we talk about is basically to do things in life and in the environment. So for example, if I were to get a light and turn it on, turning on my light, that's an example of work. Starting a car and then making it go forward and moving me around in my car, that's also an example of work. Thirdly, if I wanted to be able to move my muscle, for example, so let's say this is my hand and this is my muscle, that's also an example of work. So work is really just doing things in the environment and in the world. So the capacity to do that is energy. The default unit or the standard unit of energy is joules. So it's got the symbol J and it's spelled Joules. There's a technical definition for joules, which is talking about if you have a force of 1 Newton, so it's a standard unit of force, being applied to an object and carrying that object for a distance of 1 meter, right? That's how much like 1 joule is. But do you need to know this? Not really. What you want to think about is just joules is a set measure of energy. Okay, so now that we've talked about what energy is, let's talk a little bit about the different types of energy available. Cool. So but before we go in and talk about the types of energy, why do we need to know that? The reason why we need to know this is because in the VCE questions, what they'll often give you is they may give you a question where it asks you to describe how one type of energy is converted to another type of energy. For example, when I have a battery, let's say I want to turn on my torch. So very quickly, I've got a picture of a torch here and it shines out light. So it shines out, in this case, a blue light because my color didn't change. But inside the torch, there's 2 D-size batteries. So this is my little D-size battery in here as well. All right, so the idea is that the energy inside the battery is stored within the chemicals of the battery, and the energy that we want or the work that we want is going to be the light. So the light's going to come out of the torch. The form of energy that the light is in is different from the chemical energy or the form of energy that's inside the chemicals of the battery. So in some situations we get conversion between the two of these. That's why we need to have an understanding of the different types of energy. The second reason is because understanding the different types of energy gives us a basis of understanding the reactions that will come up in this section and in the next section. For example, when we burn fuels we need to understand how the different parts of the different types of energy in the different parts of a chemical change and how that results in, say, burning a fuel to release energy and heat. Alright, so what we'll talk about now is the types of energy. The first type is a type of energy called kinetic. So kinetic means movement in general. So let's write that down quickly. It means movement, and kinetic energy thus is going to be the energy of the movement of a thing. Okay, so if I have, for example, a tennis ball, and that tennis ball is moving in one direction really fast, the tennis ball is said to have kinetic energy. At the same time, when I have a glass of water, inside the glass of water there are a whole bunch of water molecules. These water molecules are moving around in random directions. So let me change color here and show you how they're moving around in random directions. Molecules and atoms, when they move around, they also have kinetic energy. The kinetic energy here, and in general, is expressed with the equation E equals mv squared on 2, where m represents the mass of the thing that's moving and v talks about the velocity. Right? So basically, you can see that the energy is an amalgamation of how heavy the molecule is and how fast it's moving. So if I have a heavy molecule that's moving really fast, it's going to have a lot of what we call kinetic energy. Okay, the next type of energy is known as potential energy. Potential energy is kind of, you want to think of it as stored or hidden energy, right? And it's the energy that comes around because of the relative position of this object or thing, or stresses within itself, or its electric charge, right? So this is best explained in a, like, let's think of a guillotine. So right here we have ancient, I don't know, France, wherever they use these things to kill people, and this is a big blade up the top, okay? And this is someone's head lying down. Obviously, this is a bit of a grotesque example, but it'll stick in your head. So the idea is that when I raise this guillotine here, it's got, let's say it's got a string. I'll draw the string in black. So there's a black string and it's going like this. And there's another dude here just holding that string. Okay. So the idea is when and let's like a wheel here and a pulley. So what the idea is that the fact that the normal position of this guillotine or the blade is on the floor. But what's happened here is that we've raised the guillotine up, right? So that it's hanging above this gentleman's head. The fact that it's up here, right, means that it's got a different position from its relative or normal place. So this difference in position gives it some stored or hidden energy, which means that the moment I let this go and this thing has now got the energy has now had its potential or stored energy converted into the energy of movement, and it's going to chop this guy's head off. So the same idea applies to, say, when you have a waterfall. So there's high water here and it goes down. When we have a bow, so let's say we have a bow here and I pull the elastic string here, right? That's all these are examples of potential energy. So we call this gravitational energy here, and we call this one elastic energy. The one that's also going to be important for you is going to be a type of potential energy called chemical energy. So what you want to think about in terms of chemical energy is that it's the energy that's kind of stored inside stored within a chemical, right? So it's kind of like the intrinsic energy of a chemical. And what that means is that when I have a chemical, let's draw an atom here. So it's got its protons and its neutrons in here, and then it's got a bunch of electrons floating around. Okay, so the idea is that there's a energy that's stored as a result of the attraction between these positive protons and these negative electrons. So there's some tension and there's energy there. This atom is also moving in a direction. So there's energy that comes from the attractions and repulsions between the electrons and the protons of the atom, as well as the energy of its movement. And this type of energy is a potential energy known as chemical energy. Why do we call it a potential energy? Because on its own, the chemical might not be able to do anything. But let's say I've got like a bunch of petrol in a tank. If I put like a match, right? Let's say this is a matchstick, and I stick this into the tank, right? Normally the petrol itself isn't going to do anything, but the moment I drop that in, it's going to go boom. So there's this potential chemical energy inside the bonds, inside the atoms of the petrol, just waiting to be released. And lastly, we talk about transfer energy. Transfer energy is energy that flows from one place to another place. Place. Okay, so examples of these are going to be things like heat energy. So heat is basically particles moving quickly, and then that causes other particles to move quickly and other particles to move quickly next to it. Things like sound energy, which is once again the vibrations of particles which then hit into other particles and cause them to start vibrating. Things like electricity and things like light. Cool. Okay, so now that we talked about this, we need to look at the next section. The next section is the idea of collision theory. And the idea behind collision theory, what is it? Why do we care about it? How does this relate? The idea behind collision theory is that we need a way of understanding how reactions occur. So we talked about what chemical change was, right? Chemical change in our first lesson was what was basically creating a new chemical as a result of a chemical reaction. And that involved, if we remember back, that involves the idea of bonds breaking and bonds forming. So let's refine what actually happens. We'll go over this in class, but the idea is this. We have reactant particles. Let's say the black particles here are an A, and then we've got some other reactant particles over here, and these particles are B. The idea is that these particles are moving around in random directions. In some reactions, the reactants might be moving quickly. In some reactions, the particles might be moving slowly, and there's a whole bunch of different characteristics that we can talk about afterwards. But the general idea is that these particles are all moving around in a direction. Okay, so if for example, we had a reaction which said that A plus B formed AB. Let's say that's our chemical reaction. What would have to happen in this situation for this to occur? The way the collision theory works is that it would say that in order for this reaction to occur, 3 conditions must be met. 1, these particles must collide with one another. So the particles of B must hit a particle of A. So let me highlight that in another color. Okay. Secondly, they must collide with enough energy to break the bonds of the reactants. So if, for example, we had a situation where it's methane plus oxygen to form stuff, methane looks like this. So it's got carbon bonded to 4 hydrogens. Collision theory would state that if I had a methane thing that reacted, it would have to hit the oxygen with enough energy to sever these carbon-hydrogen bonds next to them. Okay, so same idea here. So the bonds within A and the bonds within B would have to be severed and broken for a reaction to occur. And thirdly, what would have to happen is that these particles must collide in the correct orientation. Okay, so there's a specific orientation that will allow these 2 particles to react. So collision theory is simply stating these 3 postulates, and it's trying to explain to us how reactions occur. So particles essentially smashing into each other with enough energy to break the bonds of the reactants. One important idea of the last section was the fact that when we had collisions, the particles had to collide with one another with enough energy to break the bonds of the reactants. Now, let's expand on that a little bit. When we talk about the energy required to break the bonds within the reactants, we call this the activation energy, right? So when we talk about activating something, it means kind of like changing it from a dormant state to a state where it's able to do something. So activation energy is the energy required to start a reaction, okay? So energy required to start a reaction. That's the activation energy, or for reaction to occur. So what is it technically? What it is technically is going to be the energy that is required to break the bonds of reactant particles, right? But it's not just the 1 unit of energy required or how much energy is required. It is the minimum amount of energy required to break the bonds of the reactant particle. So if you are ever asked to define it, you have to have a couple of points. 1, you have to mention somehow that it's the energy required to start a reaction. 2, you have to state that it's a minimum, right? Or the lowest amount of energy that's required. And third, you should mention that it's the energy required to break the bonds of reactant particles. So if you get those three down, you've got your definition for activation energy down pat, right? So one way, if we go back to what we were looking at before, we asked ourselves the idea behind collision theory, right? How do reactions occur? And we mentioned three things. One, they had to collide. Two, they had to have enough energy to break reactant particles. So in other words, they have to have energy, the collisions have to have enough energy to, the collisions have to have energy that is equal to or greater than the activation energy. And we usually write that as EA or EACT. And thirdly, as a revision, they had to collide with the right orientation. Okay, so what we've got over here is we've got a picture here, right? So let's talk a little bit about the collisions one more time. But this time when we talk about the collisions, we're going to talk about it in terms of the heat, right, that is absorbed or released. So what happens is that when we have reactions, some reactions, when they occur, they release heat. And some reactions, when they occur, they absorb heat. So what's the deal with this? Okay, let's say in this situation we have a reaction. So we've got these particles here reacting with these blue particles over here. And basically they're going to come and, as per collision theory, smash into one another. Assuming they have enough energy to break the bonds that are holding these reactant particles together, right, or the intramolecular forces of attraction, what's going to happen is that we're going to get a chemical reaction. And as we can see in the second square here, the particles themselves have broken away. So individual atoms have broken away and the chemical has changed. So we can see that there's a chemical reaction occurring here. Now, if this reaction were to release heat, let's say that this reaction released heat into the environment, what would be happening when these particles collide? Well, the idea is that when I form new chemicals, so let's say I have a situation where I've got my methane plus oxygen combusts to form carbon dioxide and water. The idea is that within the methane and within the oxygen, as well as the carbon dioxide and water, they're going to be electrons. And electrons are going to be in particular configurations in the oxygen and methane, as well as in the carbon dioxide and in the water. Okay, so as a simplified representation, let's look at all the electron configurations. Whoops, sorry, can't say that. Electron configurations in the reactants. So if, for example, the reactants had an electron configuration where electrons were in high energy states, right? And when they were converted into the products, so when these electrons were converted into the products, if the products had, for example, the same electrons in low energy states, what would have happened is that as the electrons came and went from a high energy state up here in the outer shells down to the low energy state, it would have released that amount of energy. Okay, so when it releases that energy as the electrons go from high energy to low energy, that would be released as heat. Okay, so in this next section here, we've got three kind of terms that I want you to get familiar with. One is the idea of exothermic, secondly endothermic, thirdly delta HR. So what do these words mean? When we talk about exo, we talk about outside, right? So the way I think of this is, if you remember the movie Pacific Rim, or if you've ever seen any like mecha animes or something like Pacific Rim, or if you think of like a lobster, I can't draw, so I'm not going to draw, I'm just going to write the word lobster here. What all these things have are exoskeletons, right? And why is it an exoskeleton and not a normal skeleton? Because the skeleton is normally inside the body, but an exoskeleton mean like a lobster, like those mecha like walker things, those are going to be outside the body. So exo means outside. So thermum, right, means heat. Okay, all you have to do is think about like a thermos, right? Thermals, etc. to know that this is talking about heat. So exothermic means outside heat, which means that it releases heat into the environment. So an exothermic reaction releases heat. Okay? Whereas an endothermic, well, think of once again, let's have a look at the words. So once again, thermic means heat, and the word endo means inside. So the way I think about endo is I always think of the endocrine or endocrine system. So in medicine, the endocrine system is talking about all the hormones and all the changes that happen inside the body. So inside heat, an endothermic reaction is something that absorbs heat from the environment. Okay, so exothermic releases heat, endothermic absorbs heat. Now the last thing that we want to look at is this idea of delta HR. So when we have a reaction that's exothermic, what is the deal behind this? Well, we mentioned before that an exothermic reaction would have eventually, at the end of the day, the electrons going from a high energy state in the reactants to a low energy state in the products. And conversely, that would mean that the endothermic reaction would have the electrons going from a low energy state in the reactants to a high energy state in the products. Therefore, it needs to absorb energy to go from that low to high energy state. The question is, how much energy is released or absorbed, or how much heat is, let's say in this case, absorbed. Okay, so I might want to know the exact amount of heat that's absorbed by 1 mole of a reactant, or the exact amount of heat that's released when I burn, let's say, 10 grams of methane. So the way I express that is a unit known as delta HR. Delta means change in. Okay, H stands for heat heat, and R stands for reaction. So delta HR really means what is the change in the heat of reaction. Okay, so over here we've got 2 examples. First, let's have a look at the first one. The first one says delta HR equals positive 36 kilojoules per mole. So once again, how do we read this? Remember that I always want you to think about delta HR as asking us how much energy or how much heat is absorbed. Okay, so I look at it, I see that it's going to be written in the units. Now the delta HR value is going to be written in a particular way. We have a sign here, right? Is it positive or negative? We have a number, and then we have the unit, either kilojoules per mole or joules per mole. So for example, in the first example here, we see that this is a positive sign. The number is 36, and then the unit is kilojoules per mole. In the second example, we see the sign is negative. We have a number 117, and the unit this time is joules per mole. So how do I think about this? As I mentioned before, we think of the delta HR as how much heat is absorbed in this reaction. So the way I think about the first example is delta HR, how much heat is absorbed? Well, how much heat is absorbed is 36 positive kilojoules per mole. So that means positive 36 kilojoules per mole is absorbed. So this reaction is going to absorb, for this example's sake, 36 kilojoules per mole. That's the way I think about it. Okay. Whereas in the second example, once again, what do we see? Delta HR is how much heat is absorbed. But this time the sign is negative. So I'm thinking if I absorb a negative amount, that means I must release energy. So if I absorb a negative, that really means I am releasing energy. So the way that I see this second situation is, because the sign is negative, this is going to be absorbing negative 117 joules per mole. So that means it's going to release 117 joules per mole. Note the difference in the units. This is joules per mole, and this one over here is kilojoules per mole. So what's the main takeaway from this? What I want you to remember here is this. If delta HR is positive, so like in the first example, delta HR is positive, that means the reaction is going to absorb energy, which means that this is going to be an endothermic reaction. Whereas if delta HR is negative, right, that means that it's going to release energy, and this is going to be an exothermic reaction. So with that, we'll see you in class. And as always, if you have any questions, don't hesitate to send me a message or text me.